Alright guys, today we are going to start talking about graphing motion, and we're going to start off by talking about position versus time graphs. And over the last several days we've done two different position versus time graphs. One was for a constant velocity model, and the other was for a uniform acceleration model. So let's remind ourselves about those. So for the first graph we see here under the constant velocity model, we have something very similar to what we did in the lab. Our object started at an initial position of x equals 0, and it's moving to the right with a constant velocity. On the second graph, we have our object starting at some positive initial position, and it's also moving to the right with some constant velocity. And on our third graph, we have our object starting at some positive position, and it's moving to the left with some constant velocity. So the big thing to remember on our position versus time graph is that the slope of that graph is the rate of change of position, which is the definition of velocity. So the slope of each of these lines is the velocity of the object. And because it's a straight line, the slope is never changing, so that shows us it's a constant velocity motion. Now let's look at uniform acceleration. So the biggest thing we see here under uniform acceleration is that when our object is accelerating, the position versus time graph is going to be curved. And that makes sense because remember, our slope is our velocity. And so if an object is accelerating, then its velocity is changing, so the slope has to be changing. So we end up with a curved graph. In our first graph here, we see that it is concave up. It looks like part of a smiley face. And anytime something is concave up, that means that it has a positive acceleration. We can see that here that for our first graph, the slope starts out pretty horizontal. So our slope starts out at 0, so it's starting out with 0 velocity. And then the velocity is becoming more and more positive as the slope gets steeper. On our second graph, we start out with a positive initial position. We also start out with a positive initial velocity because the initial slope is positive. And then what we see is that slope becomes less and less positive up until this point right here. And that is when the slope of our graph equals 0. So that would actually be our object has been moving to the right and slowing down, and then right there it stops. And then it starts moving back to the left and getting faster and faster. But the entire time for this graph, the acceleration is negative. And we know that because it is concave down. It looks like a frowny face. And if we look at the first half of the graph up to the part that I circled, our velocity starts positive, but it gets less and less positive as we go. And then at the part I circled, the velocity is 0. After that, the slope gets steeper and steeper, but in the negative direction. So our slope is getting more and more negative. Our velocity is getting more and more negative as we go. So position versus time graph will be a straight line when we have a constant velocity. It will be a curved line when we have acceleration. And if it's concave up like a smiley face, then that's positive acceleration. And if it's concave down like a frowny face, then that's negative acceleration. But please understand that positive acceleration does not necessarily mean speeding up, just like negative acceleration does not necessarily mean slowing down. For our second graph here, we are slowing down up to that part that I circled. We're moving to the right and slowing down because our velocity is positive and our acceleration is negative. And then after that point, we're moving to the left and speeding up because our velocity is negative and our acceleration is negative. Alright, so continuing our graphing motion, now we're going to talk about velocity versus time graphs. So that's when our velocity is on the y-axis and time is on the x-axis. And once again, let's look at our two models of motion. Alright, so here we see two velocity versus time graphs that would fit the constant velocity model, and we can see that they're both flat lines. The top graph would represent an object that's moving with a constant velocity in the positive direction, which typically means to the right if we're talking about left to right motion. Could mean up if we're talking about up and down motion. And on the second graph, we have an object that's moving with a constant velocity in the negative direction, which would typically mean to the left if we're talking about left to right motion, or down if we're talking about up and down motion. But we can see with a constant velocity model, our velocity versus time graph is always going to be a flat line. Let's see how that looks different with uniform acceleration. Alright, so here we have two possible velocity versus time graphs for uniform acceleration. On the top graph, we can see that our initial velocity is 0. It's starting from rest. And then from there, our velocity becomes more and more positive as time moves on. So in this case, the slope of our graph is our acceleration. So this first graph represents motion with positive acceleration. We also know that it's speeding up because our velocity is becoming more and more positive. Our second graph has a negative slope, so this represents negative acceleration. We can also see that we start with an initial velocity that is positive. And then at first our object is slowing down as the velocity becomes less and less positive. But then right here at this point, we see that our velocity at that time becomes 0. So our object has slowed down until it's stopped. After that vertical dotted line, we see that our velocity starts to become more and more negative. So now it has both a negative velocity and a negative acceleration, which means that it's speeding up and moving in the negative direction. So this second graph here would represent an object that was moving to the right when we start observing it, but it slows down to a stop when it crosses that 0 line, and then starts moving back to the left and moving faster and faster as it goes. So once again, a negative acceleration does not necessarily mean slowing down. What you really want to look for is if the velocity and the acceleration are both the same sign, then it's speeding up, and if the velocity and the acceleration are opposite signs, then it's slowing down. So if I look at this graph, before that dotted line, I have a positive velocity and a negative acceleration. So before that dotted line, I'm slowing down. After that dotted line, I have a negative velocity and a negative acceleration. So after that dotted line, my object is speeding up. Of course, another way to look at that is look at the line itself. If you're getting closer and closer to 0, you're slowing down, like we are for this first half. But if you're getting further and further away from a velocity of 0, then you must be speeding up, like we are for that second half. So let's look at some coordinating position versus time graphs and velocity versus time graphs. Okay, so here we have what's commonly referred to as a stack of motion graphs for a constant velocity model. And these three graphs all represent an object that started from a position of x equals 0 and moved to the left with a constant speed. And so we see on the position versus time graph, our graph starts at 0 and has a negative slope, showing that it moves to the left, and it's a straight line showing that that speed to the left is constant. The velocity versus time graph is a flat line with a negative value, once again showing we're moving to the left with a constant speed. And our acceleration versus time graph is just a flat line at 0, because if we're moving with a constant velocity, then our acceleration is 0. Now let's look at a uniform acceleration example. So here we have a stack of graphs of an object starting at a positive position from rest and accelerating to the left. And so we can see on our position versus time graph, it is concave down. The initial slope is 0, but from there the slope becomes more and more negative. And we see that eventually the object moves far enough to the left that it crosses our 0 line and moves into negative positions. On our velocity versus time graph, we can see that our velocity starts at a velocity of 0, and then it's a straight line with a negative slope, showing that our velocity becomes more and more negative, so we're speeding up to the left. And then on our acceleration versus time graph, we see our acceleration is a flat line with some negative value, showing that we have a constant negative acceleration. So we see our position versus time graph is curved, our velocity versus time graph is straight but has a slope, and our acceleration versus time graph is a flat line. For our constant velocity model, our position versus time graph will always be straight but have a slope. Our velocity versus time graph will always be a flat line at a non-zero value. And our acceleration versus time graph will be a flat line at zero because it's at a constant velocity. I hope that makes sense, and we're about to look at some graphs of some more complicated motion.